Okay, so the last speaker for this session is Preena Samuel. So she got her PhD from this institute and under the supervision of Professor Raghavan. So she is now a visiting faculty at the Chennai Mathematical Institute. And she works on algebraic groups and representation theory. And she will speak on RSK basis in invariant theory. Yeah.
Thank you, Jaya. So I also thank the organizers for the opportunity to present some of the topics of my interest in this symposium. And the plan of my talk is to motivate a certain problem which has been of interest to me in invariant theory, and at the end of it describe a solution to that particular problem. So when I'm talking about invariance, the invariants are with respect to, I hope I'm audible. So invariants are with respect to a group action. So I begin with a brief warm-up of what are group actions. So if you have a group G and a set X, then you say that the group G acts on the set X if you have a group homomorphism from the group G to the automorphisms of X. So if X was a set, then this aut of X, the automorphism group, is the collection of bijections of this set. But typically X would have some additional structure, so you should interpret this aut X in that accordingly. So if X was a topological space, for example, then aut X would have to be the collection of homeomorphisms of X to itself. Or if X was a vector space, then it is the collection of linear isomorphisms of that vector space. Now if you have a group acting on a set X, then take any point in X, you can talk about the orbit through the point X, which I denote. So this G dot X is just, so it's the collection of points of the form. So every element of G gives you a automorphism of X. So you look at the image of the point X under each of those automorphisms and look at that collection. That's what I mean by an orbit. So a very trivial example is take R acting on itself. So R is the additive group acting on the set of real numbers by translation. So it takes X to the translate of X by the number A, and it's equally trivial to observe that this has just one orbit. You take two real numbers, you can obviously scale from one to the other by a suitable real number. And just for a bit more time spent on it, I mean just another example which is probably less trivial than the previous one, which is you look at the action of GL and R. This is the collection of n cross n invertible matrices with entries in R acting on Rn. And that's the action that we are quite familiar with. You look at the matrix acting on a tuple to get another new tuple there. And now what are the orbits? So again, this is not a very difficult thing to see. If you from linear algebra, you know that there will be only two orbits, because if you take a non-zero vector and another non-zero vector, then each of these non-zero vectors could be extended to bases. So you take the linear transformation which takes this one basis to the other, such that the first vector here went to the first vector of the other basis. Then that's the choice of G element in GL and R that takes you from one vector to the other. So non-zero vectors all are in one orbit, and the zero vector is a single orbit. So now this is the example which I am really interested in. C is the set of complex numbers, and GL and C acting on M and C. M and C is the set of n cross n matrices with entries in C. So the action is given by the conjugation action. So every given a matrix X in M and C, you take it to the conjugate by any invertible matrix with entries in C. So that's the image, I mean the what X goes to under this action. Now what are the orbits? Again, we probably have seen in our linear algebra courses that every matrix can be conjugated to what is called a Jordan canonical form. So just to recall what a Jordan canonical form is, it's a matrix of this form. It's going to be an n cross n matrix where you have blocks, and in each block you have the same scalar appearing along the diagonal, and the off diagonal is has a 1. So here there's a different scalar mu. So this is a matrix in Jordan canonical form. And what the statement is saying is that if you look at the, so let me call the orbits for this action, for the conjugation action, I call it the conjugacy class. So each orbit is a conjugacy class, and the statement says that each conjugacy class can be represented by a single element of this form. If you fix an ordering, then there's a unique choice of element in that orbit of this form. So the Jordan canonical forms are set of representatives for these conjugacy classes, or the set of orbits for this action of GLNC on MNC. So I want to look at this example in a slightly different framework, which is that of varieties. So just to make ourselves comfortable with the terms that I'll be using, I introduce what these terms are. So by a variety, I just mean a collection of points which appear as solutions to a set of polynomials in n variables. So the n is the same n that I'm looking here. So I'm trying to define what is a variety in Cn. So you look at a polynomial in n variables and look, you can talk about its evaluation at each point of Cn, where the ith variable is just treated as the ith coordinate function. So you can talk about evaluation at points of Cn and look at all the solutions for us. So you take any collection of polynomials in n variables and look at all the solutions of that collection. That is what I call a variety. Now this enables us to define a topology on Cn, which I call the Zariski topology. So for defining a topology, one needs to either give what the closed sets are or what the open sets are. So what I do is just declare the varieties that I just defined earlier. These varieties I declare are the closed sets. So these are all the closed sets in this topology, and what the topology that I get from by defining closed sets to be just the varieties is what is the Zariski topology on Cn. Notice that Cn itself is a variety because you could just take the 0 polynomial and its solutions are the entire Cn. So this is itself a variety. Now I'm trying to set up a category where I've defined what the objects are. And so if you know what the objects are, the next thing you would want to know is what the maps between these objects are, and that is what are called morphisms. So a morphism is a map between varieties, but it's not any map that you take between varieties, but it is maps that are given by polynomials. Just to elaborate a little bit on it, so if you look at Cn, it's a variety we just saw, and C is also a variety. So a map between Cn and C is called a morphism if it's going to be described by a polynomial in n variables. More generally, if I took Cn to Cm, then I would have to have m polynomials, each a polynomial in n variables. So that would give me a morphism between Cn to Cm. Now a variety is just a closed subset of Cn, so you have an induced topology. And when I talk about maps between these two varieties, I say that that map is a morphism if it's actually coming from something, the ambient Cn and Cm, so where they are sitting. So these varieties sit inside some Cn. It should be coming from that a morphism in the ambient space. So that just gives you an idea of what I'm talking about. Now I want to relook at my example that we had seen earlier. So I was looking at GLNC acting on MNC. First of all, notice that MNC can be identified with C to the power n square because it's an n cross n matrix. Each entry gives you a copy of C. So you have an identification of MNC with Cn square. So there's a Zariski topology that you have on it. So basically what you've done is realized MNC as a variety. Now once I have a variety, I can ask whether these maps that I had, so every element of GLN gave me a morphism, gave me a map of MNC to itself, and one can check very easily that each element A in GLN actually gives you a morphism between the variety MNC to itself. The conjugation action is, so basically what it's saying is that if you treat the entries of X as the variables Xij, then this matrix can be written as a polynomial in Xij's. The entries of that matrix can be written as polynomials in Xij's. Now the good thing about varieties is that there are some algebraic objects that are associated to that, which are very closely knit to the object itself. So these are what are called the coordinate rings. So the coordinate ring of a variety is formally it's just the ring of morphisms from the variety to C. So if you took Cn for example, Cn was a variety. So you're saying that the coordinate ring is just a set of morphisms from Cn to C, and what we said was a morphism was just given by a polynomial in n variables. So this coordinate ring of Cn is actually just the polynomial ring in n variables. Now, under this correspondence, one can set up a dictionary between the terms that I mentioned earlier. So, we defined what was variety and what were morphisms between varieties. So, given a variety, one can associate an ideal inside this polynomial ring. So, one captures this ideal by taking all the polynomials that vanish on that particular closed subset that I am having inside Cn, and the coordinate ring of this variety will be just the quotient ring C of x1 to xn modulo that particular ideal that I had here. Now, if I take now two varieties, I can talk about morphisms between them. So, what is the corresponding thing that I have here is a homomorphism of the associated coordinate rings. So, you have a variety V and a variety W, so you have associated coordinate rings. Now, if you have a morphism between V and W, you will have a homomorphism of rings between the coordinate ring of V and W, but the arrow will be now reversed. So, that is the dictionary that I talked about from between the terms that I mentioned earlier and the certain algebraic objects of inside the polynomial ring. Now, I want to revisit our example with this perspective. So, MNC we said was a variety and the associated coordinate ring, because this is just Cn square. Its coordinate ring is a polynomial ring in n square variables. So, xij is my, I'm indexing my variables by the xij's. And then we had a GLN action on MNC. So, you can talk about the set of orbits. You look at the collection of orbits or the set of conjugacy classes. Now that we are looking at all this in the framework of varieties, natural question to ask is whether this collection of conjugacy classes is itself a variety. And if this were a variety, then we also want to know what the coordinate ring of that variety would be. And if this, see, now we are looking at MNC and MNC mod GLN, and if this were a variety, then if there was any justice, you would expect this morphism, that the natural morphism. So, you look at any matrix and send it to the orbit or the conjugacy class to which it belongs. That gives a natural map from here to this set. Now, if this were a variety, you would expect that this map is actually a morphism of varieties. Now that you begin to see the problem now. So, if this were a variety, this MNC mod GLN were a variety, then if you look at the coordinate ring, so the elements of the coordinate ring is what I call regular maps. So, it is just a morphism from this variety to C. So, if you take any morphism from this variety to C, then you would compose with this morphism to get a morphism from MNC to C, and that is just going to be a polynomial in n square variables. Now, notice that if you have a regular map, now the point is that this polynomial, since it factors through this quotient, it means that it is going to be constant on orbits.
Do you give a topology to this orbit space?
Pardon?
Do you give a topology to this orbit space?
No, I haven't. I am trying to give, that is what is my aim. I am trying to give it a variety structure. So, if this were, so what you know is this is a morphism, and if this is a morphism, it is a polynomial in n square variables. Now, this polynomial has the additional property that it is going to be constant on orbits, the GLN orbits. Now, any map that is going to be constant on orbits has to be constant also on the closure of the orbit. That is quite easy to see, because you just look at that polynomial, look at the value that it is taking on a certain orbit, and look at the inverse, look at all the points where that particular value is taken. That is going to be a closed set in the Zariski topology. So, if a certain orbit takes if that polynomial takes a certain value on a particular orbit, then even on the closure, because the closure is going to be inside the closed set, which is defined by that particular polynomial minus that constant which you had. So, that is a trivial observation. You just think about it, it is fairly obvious that this is going to happen, that if it is constant on an orbit, then it is going to be constant on the entire closure of that orbit. So, one should probably, the immediate thing that one should check is whether orbits are closed, and the answer is an obvious no, because for example, you take 2 by 2 matrices, look at these certain matrices lambda t 0 lambda, where t is in that r cross is just a set of non-zero real numbers. So, every matrix of this form can be conjugated to the Jordan canonical form lambda 1 0 lambda, and now you look at the so which means that these are all all these elements are in a single conjugacy class. But again, one can see that the Zariski topology is coarser than the Euclidean topology. When I say Euclidean topology, there's this Euclidean metric that you can give on C and C or C par n. And with respect to that topology, so the Euclidean topology being finer than Zariski topology means what are the closed subsets in the Euclidean sense are also closed, the closed subsets in the Zariski sense are also closed in the Euclidean sense. So the number of closed sets that you have in the Zariski topology is much lesser than the number of closed sets you would have in the Euclidean topology. So if I took the closure in the Euclidean sense, that would definitely be contained in the closure of this in the Zariski sense, and it's immediate that the closure of this in the Euclidean sense contains the element lambda 0, 0 lambda, which is not in the same conjugacy class as the Jordan canonical form lambda 1, 0 lambda. So that is, so the upshot of all this is that it's not reasonable to expect a variety structure on this quotient, but rather a better candidate to work with would be not just, so instead of looking at the collection of orbits, you look at the collection of orbit closures. This probably would have a variety structure, and so that leads me to the notion of what is called the invariant ring. So if there was, if this orbit set space of orbit closures had a variety structure, one is interested in describing what the coordinate ring is for that space, and that motivates the definition of what is called the invariant ring. So you look at, so the candidate that you would think of for this coordinate ring of space of orbit closures is to look from the discussion we just had earlier, that you look at regular maps which are going to be constant on orbits. So that's going to be sitting inside the collection of regular maps of the original space itself. So that object probably is the coordinate ring, is this candidate. So this is a good choice of candidate, and so it's interesting to study this particular object which we call the invariant ring. So the invariant ring is nothing but the set of all regular maps on the original space which are constant on the orbits for that particular action that I already have on it. So what we seek is a description of this invariant ring. So coming back to our example, we had been looking at GL and C acting on M and C by conjugation. So we are trying to understand the invariant ring, that is this is the coordinate ring of Mn. This is a notation for the coordinate ring of Mn, and with the superscript GLN I mean the regular maps on Mn which are invariant under the GLN action. And this statement is again, one uses some kind of some linear algebra to see that every the coefficients of a characteristic polynomial are going to be lying inside this ring, because if you take two matrices which are conjugate to each other, then they have the same characteristic polynomial. So the coefficients are going to be constant on each conjugacy class. So they are going to lie here, and it's well known that this algebra generated by these coefficients is precisely the ring case CMN mod whatever the invariant ring, and this is going to actually give you the space of orbit closures. So this is going to be exactly the coordinate ring of the space of orbit closures. So we already described what we have got one description of what the of this invariant ring, but we are trying to going to look at another procedure of doing it, and that is interesting because it generalizes to the case of GLN acting on d copies of Mn. So this is Mn cross Mn taken d times, and GLN acting on that product by diagonally and on each copy by conjugation. So it's called simultaneous conjugation, and this is also fairly classical. It was known even from the time of Weil, which is probably more than 5 decades back. So this is all this is in this procedure that I am going to describe is in fact going to work only in the setting of complex numbers. So if I took the characteristic of the field, if you know what it is, then if the characteristic was 0, then this thing works. In other characteristic, this procedure doesn't really get you anywhere. Now the procedure says that you can get all the invariant polynomials for this particular action GLN acting on So let's just concentrate on one copy. So GLN acting on MNC by conjugation is obtained by taking restitution of invariant. So you're going to construct invariant polynomials from multilinear functions which are invariant. So what's a multilinear function? It's just a function on this product. So this is d copies, and it's going to be linear in each entry. And the fact it is going to such a multilinear function is said to be invariant if it's going to be constant on orbits. And the process of restitution is not very difficult to describe. So what you do is, instead of taking different entries, you just put the same entry. So what you get is a map from Mn to C. So take any matrix and replace every x1 to xd by that particular matrix. So it is going to give you a map from Mn to C, and the restitution. So it's known that. Yeah, so maybe a small example, if you look at the trace of, so take x1 and x2 two matrices, to look at the trace of the product of x1 and x2, then that's going to be a multilinear function in each of these x1 and x2, and that under restitution is going to go to the trace of the x square, that is square of the matrix. And yeah, so I didn't state the theorem, but one knows that in characteristic 0, this is a procedure which will hit upon all. So every invariant polynomial can be obtained from multilinear functions which are invariant by this process of restitution. So we have reduced our problem basically now to this understanding the space of multilinear invariance. So we've changed from the set of we are now not looking at GLN-C on one copy, but GLN acting on multiple copies diagonally, but now we are looking for multilinear invariance for that action. And again, this has an answer. So the answer involves what is called the symmetric group. The symmetric group is the set of permutations of, so SD is a set of all permutations of D symbols, and you can define a map from the group algebra of SD of the symmetric group to this. So this is just a fancy notation for the multilinear functions on MND, not this is just all the multilinear functions on MND. So you can define a map from this group algebra to this space of multilinear functions, and this is the map. So you look at any permutation, give a cycle decomposition of that. So this is one cycle, this is another cycle, and then define the map from, it's a theorem, this is also fairly classical, that this map theta is going to map onto the space. So here this is a notation for the set of all multilinear invariants of MND for the GLN action. So theta maps onto the space, and so what we've achieved is a set of generators for the set of multilinear invariants. So the set of generators is just the set of all permutations in SD. And as Professor Anantharaman yesterday said, when you have an answer, you want to look for more new questions, and the question we ask is whether we can find a basis among the set of generators. So what we are asking is there a set of permutations which actually gives you a basis of this space? And that leads me to my final slide, which is the answer to that problem, which says that you look at permutations having no decreasing subsequence of length bigger than n, then that gives you a basis. So look at a permutation. So say 1, 2, 3 is a permutation n as 3. You write it in a 2-line format. So you write 1 goes to 2, 2 goes to 3, 3 goes to 1, and look at the second row. If there is no decreasing subsequence of length at most n, so n should have been at least 3 in this case. So if you look at a decreasing subsequence of so if the maximum length of a decreasing subsequence is no bigger than n, then you take that permutation, collect all such permutations, that is precisely the set of all bases, set of all elements that form a basis for this ring of multilinear invariants on M and D. Okay, I should just say the space of multilinear invariance. So it's as a vector space, these are going to be a basis. So final remarks on what the proof involves. It's as we have brought in the symmetric group, this really involves the representation theory of the symmetric group and what is called its Hecke algebra, which is just a deformation of its group algebra. And this problem can be further posed in a more general setting in terms of the representation theory of the symmetric group. So this is going to involve what are called the tabloid representations. And the answer then in that general setting will involve what is called the RSK algorithm, So RSK stands for Robinson, Schoenstatt and North, and using that algorithm one can describe what the basis in this general setting is, and that is where the name comes from, RSK basis. Thank you.
Are there any further questions? So if not, we have the speaker again.
Okay, so welcome to the panel discussion. So let me tell you how we're going to do it. So these are our panel members. I'll introduce you to them. So this is Padmavati. She is from the University of Hyderabad. She's a professor of mathematics and she works in applied math. That's Ajit Iqbal Singh. She is currently visiting the institute, Indian Statistical Institute. She was formerly in Delhi University, and she is a very well-established and well-known mathematician. That's Geeta Venkatraman. She is now Dean of Undergraduate Studies at Ambedkar University in Delhi. It's a new university, and she's going to tell us about such new initiatives. That's Sujata. She's my former colleague from Tata Institute. She is now at the University of British Columbia in Canada. She works in number theory. And that's Girija Jayaraman. She is an applied mathematics person who actually was in 2 departments in IIT Delhi, both mathematics and atmospheric sciences. And she's now the head of the Center of Atmospheric Sciences in IIT Delhi. And that's Vijayalakshmi Trivedi, also a former colleague. She's still in Tata Institute. And she works in algebraic geometry. And so they are our panelists, and they're going to talk to you about the various opportunities that are available to do mathematics and science in India. And so they will each make a 5 to 7 minute presentation. And then if you have questions about their presentation, then you can ask them that question immediately. And then after they've all made their presentations, we will turn it over to you, and you can tell us ask us questions that interest you, or concerns that you might have, or anything that you like. So this will go on till 4:30. So I expect the presentations will take maybe about 45 minutes, and then we'll have about an hour to talk about things that interest you as well. Okay, so thank you. And so the first speaker is Padmavati. She's going to talk about women in universities.
Okay, so in most of the developed and developing countries, women were discouraged from pursuing mathematics for different reasons. Like for example, in the West, they were mostly considered not smart enough to pursue mathematics, whereas in India that was not the reason. The reasons were more of social nature rather than a sense of inadequacy or something like that. Most of the young girls who pursued mathematics even up to MSc perhaps became school teachers or college lecturers, and they didn't go on for research. So most of the time there were a lot of societal pressures which prevented women from returning to higher studies or a career after marriage and childbirth, and predominantly the inability to maintain or what was perceived as an inability to maintain a balance between family and work was the reason that women were discouraged from pursuing mathematics. And there were other reasons as well, that often there was a discrimination about recruiting women, and also they were asked discriminatory questions during the job interviews, and there was not enough sensitivity to create an atmosphere that was conducive to women at work. And there were not enough role models because the women did not have much visibility in the conferences or seminars or in scientific bodies which took important decisions in science and education. And of course, they could not also network much because of the family and societal, family responsibilities and societal pressures. However, a lot has changed, and presently there is a lot of awareness and sensitivity towards gender-based issues. So there's a lot of encouragement where women get to choose subjects that interest them rather than those which are considered appropriate for them. Even then, the number of women in Indian universities continues to be low, although there is definitely an improvement. And for a while, even though we lost many bright students to computer science, again we see them coming back to mathematics, that means research in mathematics, because of the attractive junior and senior research fellowships which make PhD an attractive option to pursue. Then now there are also some positive measures. UGC has made it mandatory for lady academician to be nominated during interviews, to make sure that there are no discriminatory questions asked during the interviews and there is no gender based discrimination. And there are also committees against sexual harassment to have check against gender based harassment at work. And also the advent of internet has made it very easy for people to communicate with each other, and even though they are far away from each other, the communication is easy and fast through applications like Skype, etc., and women can still interact with other researchers and prospective collaborators even though they do not physically meet them. And also there is a enhancement of the quantum of maternity leave to 180 days, which is extended even to research scholars, those who get the CSR fellowship for instance, and also they get this is also a provision for all the women employees of central government, and they can also avail 2 years of leave for child care. It makes it much more easier. Then there are also provisions for women to return to academics and research after taking a break, as you can see in this website of DST. It is called the Women Scientist Scheme, and there are also, because they constitute a very important percentage of the workforce, and there is also some schemes of INSA. You can have a look. I think you will hear more about them later. You can also see this sorry, okay. Yeah, please see this website also for more information. Some conferences were held recently which address some issues related to women in mathematics. One was held in JNU in 2009 and more recently at Hyderabad in 2010, just before the ICM. Now what more can be done? Still we find that the number of women mathematicians continues to be low in the universities, and what can be done is the following. We must catch them young. So there must be programs designed to encourage young girls even at school level to pursue science and technology and consider it as a possible career option by informing them of the career opportunities. And we must provide young students, boys and girls, to interact with the women mathematicians, and women mathematicians in turn should be encouraged to visit schools and colleges and address these young students. And we can also increase the networking and interaction between college teachers and women faculty from the universities. Further, it is required to create an awareness in the society, especially to sensitize the society where cooperation from the male counterparts is required. And we also have to provide a support system that caters to child care and improve the environment, create more opportunities for women to return to work after having children by having more projects and provide more grants and opportunities for them to return to work. And it is also required to provide child care services in their place of work in annual meetings and conferences as they do in Japan. And I feel that it is very important to have good role models among women mathematicians who can inspire young students by their mathematics as well as by their work ethics, work culture and human values practiced by them. Further, it is desirable to have more women in scientific bodies that make or review policies, advise and take decisions in government committees in policies related to science, to provide more opportunities in the form of grants, to have bodies which survey gender related problems for making proposals to government and monitoring the implementation of the proposals, and to provide more opportunities where women have more visibility, like providing travel grants to attend conferences and do collaborative research, and also to institute some awards for women mathematicians to encourage them. It is also desirable to have an association of Indian women mathematicians on the lines of AWM and EWM, which provide travel grants, organize workshops, contests, institute awards and provide mentoring of students. What do we want? We want to achieve recognition and respect for our mathematics as mathematicians and not because of being women mathematicians. We want opportunities to be able to choose or pursue research in mathematics as a career option and excel. An understanding of our needs, the problems, so as to be treated with dignity, and an awareness that provides encouragement and an atmosphere at work where we can realize our full potential. And to see a day where gender no longer plays a role in education and career, and such conferences and discussions are not needed anymore. Thank you. Yes. This is the one.
So we'll put upload all these things to our website of the conference, so you'll be able to find it from that also.
Yeah.
Okay.
There's also one more. This is of INSA. It is about training women in the IPR matters. It's not only for women in mathematics, it is for women in science.
So maybe we should move on to the next person. So that's.
I would like to thank Jaya and Vaijayanti for giving me this opportunity to be here and to be a part of this panel discussion. What I'm going to present in the next 5 or 7 minutes actually is not necessarily only for women mathematicians. It's something that all of us need to know and probably spread the word about. We've never had it so good in the last decade or so, when government, after years of not putting in money into science and technology and mathematics, has suddenly come about and changed things and started many new institutions. And what I want to do in the next 5 or 7 minutes is to tell you a little bit about these institutions. Most of you probably know about many of these places. Some of them may be new and you haven't heard of them before. And the idea is to tell you about the opportunities that these institutions offer, both in terms of for the students as well as mathematicians, and also to talk a little bit about the challenges. As Vaijayanti mentioned, I'm part of Ambedkar University, Delhi, and this was a university which was set up by the Delhi government about 2.5 years ago, and it's a social sciences and humanities university, but which decided that mathematics was core or part of social sciences and humanities. And this itself is something new. Normally when you speak to mathematicians, they firmly see themselves as situated in faculty of sciences. So as a mathematician, for me it's been very challenging to think about how mathematics interacts with the social sciences and humanities, to create courses which might be, which are mathematics oriented, but which would be open to all students, whether they were pursuing English honors or history honors, and something where they would be able to get over the kind of fear with which they left mathematics, and at the same time also to create new programs which would appeal to the mathematics community. So this is the kind of challenge that I faced or still do face at my institution. But let's see what are the other places that I would like to talk about. And of course, I've put down a list, and all the acronyms are there. There's the ICERs. So these are the Indian Institute of Science, Education and Research, which the central government has set up. The NICER. I think NICER, the difference is that NICER gets funded probably by the Department of Atomic Energy, whereas the ICERs come under the Ministry of Human Resource Development. Then there are the new IITs which have been set up. So if you do a search on new IITs, and you'll see the map of India, and now instead of 5 green dots, you have plenty of dots. Then AUD, which is the university I come from. I've put in JNU because in the last few years they've also initiated the process for starting things in mathematics, and I'll say a little bit more about it. ISIs, of course, they've been well known and have been around for many years, but in the last decade or so, they started B math programs and M math programs, which I wanted to mention a little bit about. And then I've included SNU and Flame. Partly these are also choices I've made because I know people in these places, and there may be many more like them. SNU is Shiv Nadar University, and it's a university which started functioning basically this year in Greater Noida, and they have opportunities for sciences, engineering, mathematics, liberal arts, and so on. So it's been started by the HCL group, really, and Flame is foundations in liberal arts and management education, and it's a place in Pune and has been around, I think, or was begun around 2004 or so. And these institutions, of course, they have varying entrance procedures. The joint entrance exam of IITs, those scores, KVPY scholars get admitted to some of the central government things directly. It could be based on 12th marks, written entrance examinations, and so on. Each of these institutions have their website, and the admission procedures and so on are very, very clearly given in those places. So I'm not going into them. What I want to talk about are what are the opportunities in terms of mathematics at any of these places. And what you see is now I mean, you have undergraduate honors programs which are offered at ISI, AUD, Flame, and SNU, and there are both 3-year and 4-year programs. Now, there are advantages and disadvantages. The 4-year program in SNU, for example, they don't even want to keep a criterion where they say that a student should have done mathematics in 11th and 12th. So they're seeing that first year as a year where they could possibly even allow students who may have done maths only till the 10th standard, but who really feel that they would want to pursue mathematics further, and offer bridge courses during the year and allow them to make up for it. At AUD, we have a credit-based earn your degree kind of program which has been created, where we have some core mathematics courses that they're expected to do, but along with it, the idea is for them to have a liberal education. So at the undergraduate level, you do want, I mean, if you look at the students who pursue mathematics at the undergraduate level, a very, very small percentage of them heads towards research or continues with mathematics. The bulk of the students, after doing an undergraduate degree in mathematics, move on to other things. And ultimately, this is a challenge that we face in creating an undergraduate curriculum which serves the need for, someone who wants to go and study mathematics further, but at the same time also takes care of the kind of skills that any undergraduate should have when they finish with an undergraduate degree. You also have the integrated masters, which have gone with this is the ICERs, NICER, some IITs as well, and they've gone with the philosophy that try and catch people young, so catch them young, put them through an integrated masters, and maybe many more of them will stay on in research. But I still think that, I don't know about others, but I didn't know that I wanted to be a mathematician till very much later in life. And I still feel that in any of these integrated programs, there should be a facility whereby if a student changes their mind, they could leave after 3 years with a degree of some sort or the other, and the curriculum should still take into account their general needs, and not just think that we are going to create research mathematicians out of each and every one of them. So, I mean, these are challenges that I guess the ICERs and other institutions where there are integrated masters would certainly face, and I'm sure in our discussions we'll hear much more about that. And then you also have the typical master's programs which are 2 years after a bachelor's degree, and IITs and SNU offer this. And then the PhD programs, you have them in ISI. JNU has started a PhD program 2 years ago. IITs have them, Ambedkar University Delhi has it in a limited way, and so do the ICERs and NICERs. There's an extra I there, I'm sorry. And what about the opportunities for mathematicians? I mean, as you can see, these are all new institutions. There are a large number of them, and of course there are a huge number of faculty positions that have come in. I don't know about the private universities. I think broadly they would also want to stick close to UGC regulations so that they don't get into trouble. But otherwise, if you are a person with a PhD in mathematics, this is the time to be applying for jobs. If you've got a few papers published, there are jobs wherever you want to get them. Okay, so it's never been, I don't think we've had this kind of a situation earlier before. And of course, you can also do research at these places, you can teach. If it's a new institution, you're part of policy making. I mean, I never thought that I would be in a situation where I would have to decide on the promotion policy of students or figure out what the examination system should be and so on and so forth. And I somehow feel that the kind of training that I've had in mathematics has really helped me out, even in trying to solve real life problems and policy decisions that I have to make at my new institution. And curriculum design, I mean, there's plenty of opportunity to design something different which helps all undergraduates and yet allows people to see mathematics in a new way. I mean, this is the period when you can really get into these things, and in a new institution you'll be dragged into it willy-nilly whether you want it or not. So so I would in fact suggest that being in a new institution is completely invigorating. There are no historical baggages, there are no fights that you have to keep track of, and things are being started afresh. You have a chance to really contribute a great deal in these places. What are the challenges? I think part of the challenges, and this is true for almost any institution and more so for the new ones, is we have all these goals and aims. And sometimes I wonder whether we've got the right goals and aims. But of course, new institutions at least seem to be open to reviews. Okay, so at Ambedkar University Delhi, almost every course or every program that we design, there is a constant feedback, and and I'm sure this is the case with ICERs and all the new places where you've tried something, you feel it doesn't work, you want to try and change it, or you think there are better ways of doing things. Funding, of course the government has put in a lot of money right now and it's continuing to fund these things. The private players are people who have, who at least in SNU and places like that seem to be not thinking of making any profits out of education, at least for some years to come. So funding currently seems to be reasonably assured, but what happens 10 years from now? These are things that one needs to think about. And the biggest problem, while it's a great time to do a PhD in maths and to have a few papers published and you'll get a job, it's still the matching. There seems to be a matching problem here. I mean, there are lots of jobs and probably not as many qualified faculty as yet. And once you do enter any of these institutions, and for the institutions themselves, there's a big decision to make on what should be the balance between research, teaching and administrative work. Because in a new institution, almost everybody gets involved in administrative work, and it's not something that a set of people do, and that set of people is basically all the ones who are there. Accountability. This has been a big issue in India, I think, and it still continues to be, because at one level, if you look at it and you look at the university system, there almost seems to be no accountability for teachers. How do the new institutions build in accountability as part? Is it to be only through promotions? Could we have a system whereby it comes internally from the faculty members who are part of the system? These are things that could be debated. And of course, access. I mean, India is still a country where we have a large number of people who are not privileged. They are discriminated against due to various reasons. And of course, government has norms which say that, you have to have so many reservation, there are various categories under which reservation is there. But as an institution, how do we view these things? How do we make sure that we help people who are discriminated against in terms of the policies that we make, in terms of how we transact our programs? Ambedkar University Delhi, by its very name, is a university which tries to cross these barriers of inequality and so on. And so it's a constant challenge for us that even if we take in people, how do we make sure they stay and they come out with something which is relevant and valid? And the most pressing thing, of course, is quality. I think part of the problem that all universities already face is they have programs, they have degrees, but almost any of you who've been on any selection panel will know that there's a disconnect between the degree with which someone comes on paper and actually what they know. So how do we make sure that in our programs, and particularly in the new institutions, we maintain the kind of quality that India really needs? So I'll stop with this, and thank you very much.
Based, and the students need to make a choice in the third year or fourth year
as to what
to do. They can choose between various science subjects, and they are expanding the base.
Okay.
But I don't know actually how it works in IITs.
Girija might be able to tell us something on that.
In IITs, we have a 5-year integrated program which we named as an MSc. That is, one joins after the entrance examination and goes through the 5-year program. It was initially called MSc, but all the students came and protested because when they went to the job market, they were considered inferior to others who did MTech program. So they said, we came through the entrance exam, so our degree should be MTech. So in other words, the students who pursue mathematics also want to be called engineers rather than termed as science graduates. And about the 5-year integrated program in engineering departments, after 4 years, you can get a BTech degree, provided you satisfy some credits. So you can drop out from the 5-year integrated program with an undergraduate degree, that's possible. But if you finish 1 more year, you get an MTech degree.
Has it started this year? It started this year?
And that is also like interdisciplinary, and you can choose after a year or two. I don't know if anybody from IIC can.
Yeah. What worries me a little bit is that in integrated programs, suppose there's a student who's not doing too well or wants to drop out, what is the choice? They don't have a choice, right now? It's not there. In IISA Pune as well, it's not yet. Are there plans to try and get something like that in? Not. I think Kaushik wanted to say something.
So they give a dual degree. They say we are giving BS, MS, dual degree.
Oh, okay.
They don't have a escape route
For the BS.
From the time the Hyderabad University started the 5-year MSc and the ICERs, we have been talking about get out in the middle. And all the organizations have steadfastly said, no, they shouldn't be allowed to go. If you allow them to go, everybody will go.
But somehow, I think we have to start thinking from the point of view of students and not necessarily the other way around. I mean, we seem to do it the other way around, whether it is in terms of syllabus, whether it somewhere I think students need to come into the equation batch.
Okay. Sorry, I think let's go through the presentation and then we come back to your questions. If that's okay.
Can I ask one question?